Good morning to all of you. My name is Abhinav. I'm the head of information security at Frame.io, which is a New York City startup. Before joining Frame.io, I spent 6 years in AT&T research, doing security research on IoT, cloud security, and software-defined networks. And before that, I spent 5 great years in Georgia Tech on my PhD in cloud security. And as the head of security in Frame.io, I oversee the entire security program, application security, cloud security, threat intelligence, security operations, incident response, and of course, compliance. And today I'll be talking about MLGuard, a service that my team developed to detect malicious web requests in the cloud using serverless. So just to give you a quick background on what Frame.io is, so we are the world's famous video review and collaboration platform. We allow users to upload media contents in our cloud, and then invite team members and collaborators to actually, or team members and clients to collaborate on those videos. So you can think of us as a GitHub for videos or Google Doc for videos. One of the main features that we provide is frame-accurate communication. So for example, if you can go on a specific frame and then type comments saying that, hey, change these colors or look at the fonts and so on. And those comments get actually embedded in the video itself. And then you can also annotate the video if you want to be more pictorial in your comments. And these comments can be seen in real time to your team members and collaborators, and they can perform actions. And this saves a lot of time and avoids long email threads that you have during your review process. Another thing that we allow people to create a secure hub for their film productions. It's a single place where your teams can control who can see what and when. And it also lets teams to easily organize and manage the versions of each asset. So which is, again, very important when you're working with thousands of episodic contents and you want a place where you can easily manage those videos. And finally, we allow users to securely share this content with external parties, right? Because sometimes you have to go and get approval to executives or all those people who are not part of the platform. And through our platform, you can do that. And you can also customize that how and what they will see. And again, this is very important in the post-production phase. So, I mean, these value propositions have enabled us to work with some biggest customers in the media and entertainment industry and also in the technological industries, because these days everybody is producing content. And also, this feature have made our platform target for attacks. So let's take a quick look that after getting a 30,000-foot overview, how actually it gets translated into actual platform. And this is a very simplified view of our platform, but this is relevant for today's talk. When users come to our platform, they send requests, and that request comes through the load balancer. And load balancer decides where to send the request, and we run containerized workload, and we are also moving to Kubernetes as well. And we are entirely hosted in AWS, so all the workloads run inside VPC, and we have a lot more AWS services running behind the scene, and security group and so on. And the database actually is used to store the transaction data. And there is a separate path here that I'm not showing here, which is not relevant for today's talk, is to how we talk to S3 bucket for uploading and downloading videos. Now, as I said, that it's a web-based platform, so users are sending requests, and attackers are also sending bad requests. Some weeks we see millions of attacks to our platform. Some are targeted, some are scanners running in the system, on the net. And when it happens, the best way, or one of the ways to secure or block those malicious requests, is to use web application firewall. AWS has a WAF service that we use a lot. We have developed our own custom rules on top of WAF, but we also use some managed rule services from the marketplace. And WAF help us block OWASP top 10 attacks, attacks coming from bots, and so on. And that gives us gives us the first layer of defense and block malicious requests. So when we started running these WAFs and started collecting data from web application firewall logs, and we started seeing what kind of requests are getting in, what kind of requests are getting blocked. And we found that WAFs are easy to evade. And I mean, this is not a news, we all know that, right? Signature-based systems are susceptible to evasion techniques because they are static. So once you craft the rules, you don't change that often. They are signature-based systems. So you have a SQL injection signature. They try to match SQL injection, but if you encode your input multiple times, they won't be able to parse it. And then that's why it's very hard for WAFs to detect zero-day attacks. And once we started seeing the requests in our logs that we thought that it should be blocked by WAF, they were not getting blocked by WAF, so we started looking into anomaly detection-based systems. Again, it's well known that anomaly-based systems are dynamic because they learn over time how the system is behaving, what requests are good, what requests are supposed to be blocked, and then they can easily find anomalous requests. They are more context-aware. So, for example, if you are running a Ruby or Elixir-based applications, and the scanner is sending you PHP requests, normally since WAFs don't have any application context, they will still let all PHP-related requests go through your firewall. But since anomaly detection system knows it's more context-aware, it can block those requests. It can find them anomalous, and it can alert you that some scanners are sending PHP requests. And due to this nature, they can easily detect zero-day exploits. Once you know that there is enough anomaly is seen in the request pattern, you can block it, whether it's a known attack or unknown attacks. And with this insight into our own systems, we came up with this idea of developing MLGuard. It's a serverless-based machine learning system that basically detects malicious web requests. When we were designing MLGuard, we really didn't want to create our own infrastructure footprint, right? We didn't want to run a lot of VMs or heavy machine learning systems, and then having the responsibility of managing our own security infrastructure. And that's why we decided to use a lot of serverless-based technologies as well. And that I'll show you in this talk. So MLGuard has 5 stages, as most of machine learning model or systems have. In the first stage, we collect logs. Logs will help us build models. And once we have the model, we deploy the model. And then using those models for future requests, we use, using the model for future requests, we decide whether it's a good request or bad request. And when there's an anomaly, we notify to security team that this IP is sending bad request when it crosses the threshold. And all these stages use serverless technologies in our pipeline. So before we look into MLGuard, let's take a quick overview of what kind of serverless technologies we are using. So we are using mainly functions as a service, and since we are entirely hosted in AWS, we are using AWS Lambda extensively in our platform. So when in the beginning, cloud providers were offering IaaS services, they still offer, but in the beginning, it was the only service that is being offered, where hardware and hypervisors were managed by cloud providers, and virtual machine, operating system, and app was the customer's responsibility. In the platform world, it got changed a little bit because now hardware, hypervisor, and the virtual machines are being managed by cloud providers, and containers and applications were the responsibility of customers. They have to do patch management. They have to make sure that vulnerabilities gets addressed, and so on. But this got pushed to an extreme in the function as a service world, where now cloud providers are managing hardware, hypervisor, virtual machine, operating system, and even the runtime. So you don't have to, as a customer, you have to just bring your code and start running it. So if you want to develop Python-based application or Java-based application, you don't have to worry about setting up the runtime or setting up the environment. You can just bring your code and start executing it. And that way, we don't have to worry about patching our own infrastructure. You can transfer this responsibility to the cloud provider that those VMs or machines are properly managed and secure. And you just have to worry about the security of your own code to make sure that you don't have any bugs in there. And there are several benefits of using serverless, right? First, so as I said, there are no servers to manage, so you don't have to worry about patching or securing those machines. You don't have to worry about the scaling of those serverless functions as well, because if there is if at the peak demand, if you want to run thousands of concurrent execution of your servers, cloud providers will do that. You don't have to set up automatic scaling group and so on. It can help you save cost because it provides fine-grained metering. So you are going to be charged on each invocation of your functions, so you don't have to worry about that functions are, unlike VMs where you have to pay when the VMs are running, whether they are processing the workload or not. Functions, you only pay when they are invoked. And it's a faster time to market because, again, you don't have to worry about the environment. So we use serverless a lot in our entire infrastructure. We have a transcoding pipeline where we transcode videos using serverless and step functions, and in security team is using a lot. And based on our extensive usage, we came up with six different design patterns for serverless. We even wrote a research paper last year in Hot Cloud that describes all the design patterns and how those patterns came together in our threat intelligence system. But in this talk, for this talk, I would like to cover two patterns that we are using a lot in MLGuard. So one is event-driven, and one other is periodic-invocation. They are very easy to understand. Event-driven functions are when these functions as a service or Lambda functions get subscribed to events. So for example, Lambda functions can sit on top of S3 and listen for all the put objects operation. And as soon as objects are stored in the S3 bucket, this Lambda function gets invoked, process the event, and go back to sleep. And this kind of functions are very useful because you only pay for their invocation, so you don't have to, so that saves cost. And also, you don't have to do polling because they are only being invoked when the event of interest is actually happening. And S3 is one example. You can also Lambda functions can also be attached to DynamoDB. So tables. So whenever you add new entry, these Lambda functions can be invoked to process those added rows. Periodic invocation serverless functions are nothing but think of it as a glorified cron job, sort of, that we have all used in the past. So they are invoked periodically, every minute, every hour, daily. They can be customized. And when it gets invoked, it performs its job, and then uses some asynchronous mechanism or sometimes email to pass the result to the results to the function that is calling, or to the service that is calling. And that's very useful. For example, if you want to develop a service that is using LRU-based algorithm to transfer data from S3 to Glacier. These Lambda functions can be invoked once in a day, look at the LRU policy for each uploaded object, and basically transfer to Glacier. Since we, as in our platform, we allow users to upload media contents, right? So we have a petabytes of storage, right? So for us to save cost, we would like to we have these kind of Lambdas running that can transfer data to Glacier to save cost. And this is also good for compliance purposes, because daily we want to check whether our infrastructure or services or cloud configurations are compliant for SOC 2 or for other compliance framework that we are part of. So with this information, let's look MLGuard again. So again, 5 stages, and collect, build, deploy, prediction, and notify. The first step is that how do we collect logs, right? So MLGuard, as I showed you in the first slide, that all our incoming requests hits the load balancer. So MLGuard works off with load balancer data. It's very similar to web logs. It has all the fields that you normally find in the web logs, and since it captures all the interaction with the customer, we are using that log to train the model. And all the logs are provided by AWS, so these logs are actually stored in the S3 bucket, and we call them raw logs because that's the log that AWS provides. But then we use event-driven Lambda functions on top of this S3 bucket and this Lambda's job is to enrich the data that we get from AWS. So enrichment, for example, ELB logs have IP addresses, but we enrich the data by adding geolocations in it. It has IP addresses of our instances or VMs, but then we attach security groups or other important informations that we have in our environment to that entry, so that it becomes enriched. It has a lot more context, and that's going to help us train the model and find problems when we look at the logs. And then this Lambda function stores the enriched data into another bucket or another prefix in the S3, and we also pass this data to Elasticsearch. So we use Elasticsearch as our SIM, so it can help us create graphs, visualizations, and even when we want to, in case of attacks, we can easily go to Elasticsearch and see what kind of requests were sent. Once we have the log, then the next step is to what algorithm should we use to actually build a model. So there are supervised algorithms in machine learning. There are unsupervised. There are reinforcements, right? So supervised, we need label data, but it's very hard to get the label data in the security world, right? Because you don't know all the attack patterns, right? So we resorted to unsupervised learning, right? Because we don't need label data for that. But it does require us to have a huge amount of data set, right, to train the model. Luckily for us, we get millions of requests every day, so millions of logs, ELB logs. That is good and sufficient enough for us to train the model. So we use unsupervised learning to basically find the anomalous requests sent by attackers. So it becomes an outlier detection problem, right? Find the needle in the haystack. So we use isolation forest algorithm. It's an outlier detection algorithm whose job is to find anomalous point from a given distribution by creating ensemble of binary trees, right? So in a nutshell, without going too much into the details, and we can talk offline on that, the way isolation forest works is it's very intuitive to understand that it basically finds outlier, right? It finds whether the point is anomalous. So the way it does, it basically creates cuts in the data set. So if you or splits. So if in a few splits, if you can isolate a point, means point is an outlier, right? So think about in this point, if you take a one cut and the point is off, then it means an outlier. But if you are using 10, 15, 20 cuts in order to split the data and isolate a point, means that its point is normal, right? That's what is shown here, that if the red point is in 3 cuts, we could isolate it, it means that it's an outlier. But the point red on the, in the center, we have to go through almost 7 and 8 cuts, and it means that the point is not an outlier, it's a normal point. And that's the basic idea behind isolation forest. Now we have data, we have models, so what features do we need to use to train the model? And the idea that we want to come up with, that we don't want to know individual HTTP requests or individual requests, whether they are good or bad. We want to know whether IP is good or bad, right? And we can find it out based on what kind of request is being sent by that IP. So on the left, if you see that if IP is sending a lot of 200 requests, 300 requests, which are supposedly good, and very few 400, 500 requests, which are signs of a bad request, forbidden or internal server error, means this IP is overall good IP, right? But on the right side, if an IP is sending very few 200, 300 requests, but a lot more 400 and 500 requests, it means that that IP is either scanning, they're trying to find its way, and that's where they are getting denied so many times, means this IP is bad. And that's when we want to look into what that IP is doing so that we can block it. So the next step is to build, train, and deploy model. And for this purpose, we use AWS SageMaker. It's a machine learning as a service that AWS provides that makes your job a lot easier in terms of build and train and deploy model. Once our algorithm was ready, in few hours, we could have our system up and running using AWS SageMaker. And there, we are using, again, a lot of serverless technologies. So here, we are using periodic Lambda invocation. So what we did, once we know we are using isolation forest and we are our model was coded, we containerized it, right? So, and published into the ECR, and wrote a periodic Lambda function whose job is to wakes up every 24 hours, run the container automatically, and container talks to the enriched ELB, gets the enriched data from S3, retrains the model every 24 hours, and deploys the final model in the SageMaker. There is no manual intervention at all. A model, every day, this Lambda function is training the model automatically. And once the model is trained, it is running in the SageMaker, and that's when we go to the prediction stage. And what happens when you deploy model in SageMaker, it gives you an HTTP endpoint that you can directly invoke, and it can tell you whether the request is good or bad. So again, we are using periodic Lambda invocation that invokes every few minutes and looks into the recent request that was sent by IPs, and it gets the model from the database and starts invoking the model with the HTTP request or with the collection of HTTP requests based on IPs, and started querying whether this is a good IP, bad IP, good IP, bad IP. And SageMaker tells us that, our model tells us that the results. And if the predictor Lambda finds out that this is a bad IP, we get notified on Slack saying that this is the attack going on, or this IP is sending bad requests, look into it. And through Slack, we can, again, automatic response we can take. So this is a notification to security analyst. Due to, I took some details off from this alert. Those who are interested, I can show you offline. So it says that anomalous IP, this IP is anomalous, and we post a link to our Kibana Elasticsearch dashboard. If you click on it, you can directly go to Elasticsearch and see all the requests sent by that IP in the last few minutes. So you can see that in real time what is happening. Then we show the IP, But we also add IP's reputation along with it. So if you click on that IP, it can take you out, to the reputation website to show you whether this IP is part of blacklist, part of email spoofing, is from China, is from Russia. You can know all those things. And we also have a geolocation, but geolocations are changing sometimes, so you have to keep updating your geo IP database. And we have a block list, and the triage list means that if you triage means that, okay, you looked into it, you ignored it, but if you say block, we can directly block. If you click on this thing, webhook gets fired, that invokes few other Lambda functions, and we directly add this IP to our web application firewall list or block list, and that's when this IP is blocked automatically. So few metrics related to our system. In the last month of October, through our system, we blocked 339 IPs alone that were basically flagged by our system. And when we found out that these IPs were indeed sending bad requests, so we blocked them. It's not an accurate, and 527 unique IPs were reported by MLGuard. So if you look into the percentage, it's like a 65% of IPs that were reported, we actually blocked them, but that's not an accuracy test because sometimes MLGuard still detects that this IP is a bad IP, but for a business reason, we decide not to block it, right? Because they are either hitting our rate limiting violation, and we do want them to still test it, but we looked into it, but still want them to go through. And sometimes MLGuard identifies problems in our web application, right? That we go to developers and tell them why we are sending this error code when we are supposed to sending some different error code to end user. And that's when it's very good for our developers to see that what's going to get a real insight on how what kind of problems are within the application, so they can fix that. So the key takeaway from this talk that it used to be very hard to develop machine learning-based systems, right? You have to spend so much hours, days, months to build, train, and deploy models. But in the cloud, with the serverless and with the machine learning service, this becomes very easy. We are using a lot more algorithms right now in our pipeline or in our layer defense that are AI and machine learning driven rather than just signature-based driven. So do try it out. I mean, it's like developing, integrating these kind of services with serverless and services are possible and is the way forward. Thank you.